Okay, so good morning to all of you. Am I audible?
Good morning, sir.
Yes, sir.
Good morning, sir.
Good morning, sir.
Okay, so today we'll continue with crystal structure, and this is the point where we'll start. We have discussed about plane and directions for all cubic unit cells. So today we'll be discussing about the HCP structure, planes and directions of HCP structure. Now, here slightly different approach is considered because the geometry of the HCP cell itself is different. Since we have hexagonal plane, so we'll have to consider three-dimensional horizontal axis, three-dimensional axis. Apart from that, you will have to have dimension in the vertical direction to denote the height. So just see here in this diagram. Here we call the indices as Miller-Device indices. We have only discussed about the Miller indices for cubic cells, but in case of HCP, we call it MB indices or Miller-Device indices. The difference or the additional feature is that we will have to consider four axes, A1, A2, A3, and C. And the process is same, and four indices are denoted by HKIL, HKIL corresponding to A1, A2, A3, and C axis. So that is the difference. Instead of three, which we have considered for Miller indices, we consider here four indices to denote the unit cell, and notation is HKIL. So if you see the geometry here, you see in the hexagonal horizontal plane, the lower plane, we take the center point as origin, and we denote the different axes A1, A2, A3 as usual, positive direction, negative direction. Suppose A1 we consider in this direction as positive, you see as shown in the diagram, plus A1, then obviously on the negative side it will be minus A1. And similarly, plus A2 on the right side, let us say, then minus side it will be minus A2, and like that. So it will be A3 plus A3, and this direction it will be minus A3. And with reference to this origin, if you go towards upper side, it will be plus C, and if you go towards the lower side, it will be minus C. That is the notation. So with reference to origin, we will consider four axes, and we will denote the axis as usual, plus minus. Now, if these people are so late in joining, then it becomes a problem, Continuity is hampered. So, HCP crystallographic directions. Let us first see the directions and how to find out the directions. So, as usual, what we do, number one, we try to reposition the vector if required, because we try to keep the keep the origin at the center of the lower surface, and if the vector is not positioned here, Suppose if you can consider any vector within this unit cell, but you'll have to then position it. You'll have to position the vector such that its tail is coinciding with its origin. Then it will be easier. We'll see some example. So let us consider this vector. It starts from here and it is just on the right hand side direction along the, let us say, minus A3 directions. So how will I decide the crystallographic direction? So these are the steps as usual. So the vector is repositioned to pass through the origin. First thing it is to be done. If it is not passing through the origin, then read of the projections in terms of the unit cell dimensions A1, A2, A3, or C. Adjust the smallest integer values and enclosing the square brackets. And here we consider a different, or sometimes another. Here we have used a different variable. The purpose of using these variables you will understand in the next slides. We denote the variables u, v, t, w. So this is the 4 variables we use, and we keep it in the third bracket. So it will be the directions. So here for this direction, let us say from origin to on the right hand side, it comes up to be 1, 1, 2 bar 0. So how it has come, let us see. So this is the direction. So it is in this direction. So if we just take the top view, then it looks like this. This is hexagonal plane, and this is the green color arrow. This shows the vector. So what we are taking, we are basically taking the projections of this vector in A2 and A1 directions. It is parallel to parallel to this A3. So we need not to take any projections on that. So what it comes out to be that this is the length of the vector along the A2 directions. Then similarly, this comes out to be the length of the vector in the A1 direction. So once we get these projections in the respective directions, then as usual proceed. We adjust this to smallest integers and we enclose it in the bracket. So let's see. So it comes out to be half, minus 1 and 0. So if you convert it into integer or smallest integer, then it comes out to be 1, 1. And since minus is there, so we give the bar sign. So 1, 1, 2, 2 bar 0. So that is how it comes out. That is how it is. This direction is determined here. Now another important part here that is to be understood. Now if you are interested, you can see the proofs. Proofs are there because here I have not added the proofs. Actually in blackboards it is easier to show the proof. If you are interested, it is there. If you just search in Google, you will get the relationship. This particular relationship is that when you have got a device direction that can be converted into a hexagonal direction by using this relation. What are the relations? Let us see. We'll consider the 4 parameter MB indices, Miller device indices. So as you know, 4 parameters are there, and those are denoted by U dash. Those are denoted by UVTW, 4 parameters, and the corresponding device indices we are considering as U dash, V dash, W dash. So we have a relationship. What is the relationship? Relationship is that U equals to 1 by 3 to U dash minus V dash. V equal to 1 by 3 to V dash minus U dash. P equals to minus U plus V, and W equal to W dash. So this relation, proof of this relation is there. You can see it is there. If any clarifications are there, if you need any clarifications, you can discuss. Then I'll have to prove it here. I'll have to show it. I can say if you need clarification, I can show you the proof. It is quite simple if you consider the just. How will you perform this proof? Just see. This is the relationship. Now Next, let us see the next slide, then it will be clear how we are going to compute the MB indices from the given just Miller indices. What we do is that this is the total unit cell, HCP unit cell. Out of this unit cell, we are considering only a portion of this unit cell. A portion of the unit cell in the sense, let us say we are considering only A1, A2, and Z direction. So these three vectors we are considering as our reference dimensions, and we are trying to determine what are the values of U dash, V dash, W dash corresponding to this A1, A2, Z. So in this particular direction here, you see we do not have this A3. So we do not have the A3 here. So this 2 bar is directly omitted. So we are getting here 110. We are getting here 110. So U dash, V dash, W dash becomes 110. So the value of U dash equal to 1, value of V dash equal to 1, and value of W dash equal to 0. Now we are just applying the conversion formula U, V, T, and W, and we will get the MB indices. So basically here what we are going to assume is that we confine ourselves to the revised parallelepiped. That means you are considering only a portion of this hexagon, considering the three dimensions A1, A2, and Z. So that is how we can easily perform the conversion. This from Miller indices to Miller revised indices can be this direction can be converted in this formula. So that is how it is done. Now let us see some of the examples, further examples. The hexagonal unit cell. Let us say we want to denote the top surface by Miller indices HKIL. So as usual, we will take the intercepts A1, A2, A3, C, and we will take the reciprocal of that and keep it in your first bracket because it is plane. So we will keep it in the first bracket. So HKIL, it will be 0001. So this plane will be denoted by 0001. As simple as that. So similarly here, another example, say we want to find out the MB indices for ABC plane, ABC, the frontal plane, ABCD. So first we'll have to see where it is intersecting the axis. So it is intersecting at plus A1 at plus 1, A2 at infinity, A2 at infinity, A3 at minus 1, and C at infinity. So take the reciprocal and
Sir,
yes.
sir, can you repeat that why A2 is equal to infinity, and for the first one why A1, A2, A3 are infinity?
For this, okay. So intercept A1 equal to infinity because you see, we are considering this plane, top plane, okay. So if you extend this top plane, will it intersect the A1 axis? Where will it intersect?
Okay.
It will intersect at infinity. It is parallel, na?
Mm-hmm.
Parallel to A1. So we are assuming that it will intersect at infinity like that. Clear?
Okay, sir.
So similarly, you can find out other planes also. You can just take it. So here we have shown for different planes. You can just take it. It is quite simple. It is not a problem. You can understand. Now slightly you have to think when the planes are inclined. Let us say. So here are some examples of directions. You see here are some examples of directions. Here are so many examples are given. Here in the first diagram, you have been shown three directions, all passing through origin. Okay, so it is done like that. But if it is not passing through origin, then we can make it to pass through origin by taking a parallel vector. So that is to be done first. That is the condition, that you'll have to draw the vector in such a way that the vector should pass through the origin. So you should check yourself if you have any confusion on this. I have told you the explanations, and you check yourself. If you have any confusion, then we can further discuss. Otherwise, I think the concept is clear. It will be clear to you. Now, just see this diagram, this one. I have here shown a particular plane which is, it is not, it is slightly, inclined plane. It is not parallel to any surface or any given plane of the hexagon. So you'll have to look it carefully. So here, this plane, the method is same. You'll have to just see where this plane is intersecting the 4 different axes, A1, A2, A3, and C. So if you look at this plane, you see I have not given any notation in form of A, B, C, D, something like that. From the diagram itself, it is clear. We are considering a plane, this plane at the base. Here it intersected the A1 at this particular point and minus A3 at this point. And the top surface, if you see, it has passed through the center. That means A1 is equal to +1 because it has intersected here. And if you look at the point where it has intersected A3, it is at minus, A3 value is -1, somewhere here. So A3 you have got -1. Now if you look at A2, where it has intersected, you see A2, yes, it is parallel. It is parallel. So it has intersected at infinity. So take the reciprocals, and accordingly, as usual, you can find out what is the MB indices for this particular plane. So this is the method by which you can determine the direction and planes, different planes, using the indices, MB indices. Next point is linear and planar density calculations. You know how to calculate the volume density, but sometimes you require to calculate the linear density and planar density also. It is also quite simple. You have to consider the effective number of atoms or diameters along a particular direction to get the linear density, and you'll have to calculate the effective number of areas or areas in a particular plane to get the planar density. So linear density, why it is required is that it will give you some idea about how many atoms are there, in a particular direction. And as we have already seen at the beginning, I told you that the mechanical properties actually indicates, or it may, like elastic modulus, as the number of linear density increases, the linear density value of linear density increases, the elastic modulus mechanical properties value is going to be more, because it will, you'll have to dislocate, or you'll have to move more number of atoms in this and in that particular direction. So we have seen in the in some diagram earlier, so we'll see it later on also. So that is the indication. That is why we want to calculate the linear density in a particular direction. So so that we know what is likely to be the magnitude, relative magnitude of a particular mechanical property. So linear density. So linear density is the number of atoms, or you can say the number of diameters, because here, if you consider a particular direction, in diagonal direction of this particular face, if you see here you have got the 2 atoms with 2 diameters. So we'll consider 2 number of atoms divided by length in that direction, unit length in that direction vector, length of the direction vector in that particular direction. So that will give you linear density, just as it has been seen that if you take this direction as shown here, 1, 1, 0 direction, so you are getting 2 number of effective number of atoms divided by the length is root 2a. So that is how you calculate the linear density. Similarly, the angles are also sometimes required. Anyway, this formula you know from your 3D geometry idea. So if we want to find out the angle between two different planes, that is also required. Sometimes it may be required. Then comes the planar density. So planar density means you have to calculate the density along a particular plane. So here also you have to have the idea of effective number of areas, number of atoms. So here we have assumed here, just see here, we have assumed a unit cell of, it looks like body center. So if we consider a plane, this plane, let us say, top surface. So if you take the top view, it looks something like this. So obviously we are interested in this, area. So we see that the effective number of atom here in terms of area, it is only 1, and we get the area. If we know the lattice parameter A, we know the area, A square. So it gives you the idea of planar density, how many atoms are there in that plane. Now, if the planes are in different, different orientation, then you'll have to properly think how to find out the actual number of, atoms in that present in that plane. Say in this, yes. কোনটা কোনটা এটা 2 ডাইমেনশনাল আছে, 2 ডাইমেনশনাল বলা হয় 2D 2
ওইটার
ডাইমেনশনাল
রিপিট হচ্ছে বলে বারবার সেই জন্য বলেছে ওটা ইউনিট সেলটা।
হ্যাঁ 2D এর জন্য এটা বলা হয়।
হ্যাঁ স্যার।
আচ্ছা নাও প্লেন অ্যান্ড ইফেক্টিভ এরিয়া অফ অ্যাটম। এবার প্লেনটা যদি একটু অন্যভাবে হয়, ইফ ইট ইজ স্লাইটলি ডিফারেন্ট, জাস্ট সি হিয়ার we have taken a diagonal plane. Then you have to have a proper view, proper diagram, so that you get the idea about how many atoms are there in that plane, effective number of atoms. So if you take the view perpendicular to this plane, you will get this view in right hand diagram. So from here you can get the idea about how many atoms are there in that plane. That also, because you see why it will be required when we will be talking about the dislocation motion of defects. It is 2D defects. We will discuss that, imperfections of solid. See, these are very important idea to give you that how much force or the stress, whether it is shearing stress or normal stress, will be required to move the atoms. So obviously, suppose I want to slide a plane along a particular direction. So if effective number of atoms are more in that plane, obviously I require more force. Indirectly it will give you idea of some mechanical property, whether it is you consider the tensile strength or hardness. Means hardness, basically that is the thing, that when a metal deforms, then only it will be softer or harder. If you are not able to deform the material, that means the material is harder. So that way it will give you some idea. So that is how it is related. These ideas are related to the mechanical properties. So here you see we have 2 number of atoms in this area. So obviously 2 divided by total area, then you have to calculate the area also, effective area. Once you know A, so area is becoming root 2A into A. So that is how we'll calculate. So this is the planar density for this particular plane, along this particular plane. So the plane is 110. Now same thing will be changed if I tell you to calculate the planar density along a plane 111. So you'll have to visualize the 111 plane, then you'll have to see how many atoms are effectively there on this plane, and then same idea is used to calculate. Just let us see here. Yes, here just see. So when you are taking a plane along 111 plane, So we can have different idea. So if you consider a unit cell, then you'll have to properly see, although it has been shown for different planes actually in different so many. So here you'll have to select the unit cell. What is the unit cell? So if is the smallest cube is the unit cell, then accordingly you have to see how many atoms are there in that plane, and you have to see what type of structure first, whether it is simple cubic, face center, body center, like that, and then you have to see how many atoms are there. Here it is discussed in general. It has been discussed in general because what we can see, it is a simple cubic structure. It is a very simple cubic structure. There is no central atom. Only atoms are present at the corners of the cube. So for that we can calculate it in this concept. So now here you see there is a concept called interplanar spacing between parallel planes. So this is denoted by DHKL. So if you are considering a plane, let us say HKL, and you want to know the interplanar spacing, then it becomes A divided by root of h square plus k square plus l square. Actually, this is what we can find out by XRD analysis, X-ray diffraction. You know, we use the Bragg's law. I am not going into the details because that requires some more discussions. You can see any, net how to, basically it is material characterization technique. What we try to understand is in a particular plane, along a particular plane, what is the interplanar
Sir?
space?
ওটা ব্র্যাগস ল বললেন নাকি?
Bragg's law. It has got a
আচ্ছা।
formula. Due to the Bragg's law, that principle of XRD diffraction is Bragg's law. We can just see in net, and we try to determine this, D, to know the interplanar spacing. So for a particular arrangement, this D value is constant for a particular type of material. So if you want to know the interplanar spacing for iron or say copper or any metal, we can identify that metal actually by knowing the interplanar spacing. So it is used to identify if there is a mixture, you see, or say alloy. So what are the elements are there in that alloy? By knowing the, this D value, we can sometimes determine what is the likely material. There it can be directly determined because there are some reference guidelines, some reference data is there. So suppose a sample is given, you put the sample into XRD device and you collect the data, the output, and check with the available, reference book, and then you will be able to identify the material that is present in the unknown sample. That is the idea. So this is a very, very important part for material characterization. Next part, we are coming to the ionic crystal and ionic packing factor calculations. It is similar to what we have discussed for metallic crystals. Only thing is that here we can think of different, elements. In a metallic structure, it can so happen that the same type of atoms are present in the unit cell, but here you will get the different types of elements having different radius and so on. So this idea, this coordination number, the number of lattice points closest to a given point or reference point. So this plays a very important role. And another important the parameter which decides the geometry in case of your ionic crystals is the relative size. Relative size means the ratio of radius of cation and anion. So coordination number and ionic radius or the relative radius, this ratio, this ratio is sometimes called the relative size. So this you have studied in your chemistry classes, I know. So let us say we have got this coordination number 2. Coordination number 2 means a reference atom is there and you have got the 2 atoms nearby, then likely structure is to be linear. That is the idea. And from the calculation, we find that this relative size R cation divided by R anion will be definitely less than 0.155. So this proof you must have done at your plus 2. I am not going to repeat. Then if it is triangular, so if this figure is not clear, geometry is not clear, you see the bigger spheres touching each other, and in between there will be a space which is called the interstitial space. So there is a possibility, or you will have to place a very small atom in this interstitial space here. So if the radius of that atom is smaller, let us say, or cation, let us say, we are putting there. Normally size of cation is smaller than the anion, and the size of anion is the bigger sphere, radius. So you are getting the relative size. So if you want to form a triangular structure, triangular geometry, then your relative size is going to be going to have this value. So what is the point? Point is that if you know the relative size or this ratio, and if it falls in a particular range, you can at once determine what is its coordination number. You can determine the coordination number. You can conclude what is the likely geometry, how the atoms are arranged. That you can conclude, and from that you can perform all sorts of calculations, whether you are going to evaluate a particular physical property or other types of, you want to have a look into the unit cell structure, everything you can do. Say for example, I know the radius of cation and I know the radius of anion. This data is available in any material science book because the scientists have already determined all this by experiments. So those data are available. And if you take the ratio and if you get the value lying within this, say 0.225 and 0.415, you will conclude that the structure is tetrahedral and coordination number is 4. And here one example we have given here. Let us consider that ZNS, zinc blend, ZNS, zinc sulfide. So point is that we have got 2 different types of atoms here, zinc and sulfur. And zinc is obviously the cation, sulfur is anion. So what will be the positions? Here very important question. I will require you to think about the position of sulfur ions and zinc ions in this unit cell, where those ions will be located within this unit cell in terms of geometry, in terms of let us say x, y, z dimensions. That is very important. Another point, at this point I can tell you, if you see diamond, you see diamond will also have this type of structure, tetrahedral structure. So ZNS and diamond will have similar type of tetrahedral structure, and only difference will be that at all the points in the tetrahedral structures, in case of diamond, will be the carbon atoms. Only the carbon atoms will be present. But here, in case of ZNS, some of the points will be occupied by Zn, and some of the points will be occupied by sulfur. My question is, which points will be occupied by Zn or zinc ion or cation, and which points will be occupied by anion? That you should think about. And probably I may ask you some question on this. And once you know the geometry, then only you will be able to calculate what will be its likely density, theoretically from the atomic structure of view. And other things also you can think about. So this geometry is slightly complicated. You have to think about, then you can get the idea of diamond structure also. So this is tetrahedral structure, and how come this cation anion ratio will be within this, that you can decide, you determine. I think you know that, you have studied. Then comes your another important type of structure. These are all basic structure. That is called the octahedral structure. For octahedral structure, you have the coordination number 6 and the radius ratio range is 0.414 to 0.732. So if this radius ratio or relative size lies within this range, then obviously you can conclude the coordination number will be 6 and the type of structure or configuration will be octahedral. So this is one example here I have just given. Any common example, NaCl, sodium chloride. And sodium obviously will be the cation, chlorine anion. So which are the octahedral points? You see, you have to locate the octahedral points. Similarly here ZNS also, which are the tetrahedral points? Just see this, again I am repeating this ZNS. You see, the zinc atoms which have been marked by blue color and smaller in size, they are located at tetrahedral positions, and I question is which are the which points are called the tetrahedral positions. So if you go inside into this unit cell, you will find the total number of tetrahedral points within this unit cell will be 8. I am repeating, total number of tetrahedral points within this unit cell will be 8. But point is that you cannot put or place all the Zn plus, all the 8 Zn plus cations, Zn plus ions at all 8 tetrahedral positions. Then it will, because of the geometry, you won't be able. Then question is, which are the points which will 50% of the points? That means out of total 8 locations or 8 spaces, only 50% will be occupied by zinc ions. So that is why you can see here only 4 number of zinc ions are there present in this unit cell. So 4. Now point is that how these zinc ions, cations, will be present in this unit cell. That is what I am asking you to think. And then you come to the sulfur ions. You see, if you look at the sulfur ion, it is, you can see it is basically face-centered cubic cell, face-centered. The sulfur ions or the anions are actually present at the face center. So you see at this particular right-hand side face, you have 4, and on the center of the face there is 1 sulfur ion. So that is the tetrahedral structure for ZNS. So in terms of geometry, you should think about it. So next is, let us come to the octahedral structure. Octahedral structure, when you are talking about, then which are the octahedral position? Octahedral position in this unit cell, you see, you have got the 12 edges total. You have got the 12 edges. So center of the edges of the cube are the octahedral positions. So the Na ions or sodium ions will be located at the tetrahedral positions, and you just see the chlorine atoms where they are located. They are located at the face center. They are located at the face center. So once you know the position of the atoms and effective number of atoms, then only you will be able to calculate the some parameters like what is the ionic packing factor, then density of this particular material, and so on. So these are the structure. Then comes the simple cubic structure. So cubic we have already discussed. So if you can see, this is another example, say cesium chloride, CaCl. So cesium here will be plus and chlorine negative. So cesium will occupy the central position or center, and you have got the 8 number of atoms at the corners. So this is the structure. So here the point to be noted is that for ionic materials, the geometry is very important. Knowing the geometry is very important to know the structure, and once you can visualize the structure, you will be able to calculate some of the required parameters, and you can get the idea about the property of the materials and so on. So there can be different types of crystal structures for ionic materials. This is one particular type of structure which shows a simple cubic. Already it has been shown. Then this is another type of structure, NaCl. Already you have discussed. There are some more examples here. Then zinc blend, that means ZNS. So this is the structure. This is just like diamond structure. Again, I am telling. Some other examples like silicon carbide. You know, these are some of the materials which are extensively used for, like silicon carbide. You know, you use it for developing the cutting tool material, silicon carbide. So this is the structure. See, we have got a large range of materials, but we won't be able to discuss all the materials, but we are only just touching on some of the important materials we use. Then another type of structure which is called the perovskite type of structure, perovskite crystal structure for this ionic materials. This is AMX3. X is the halide, M is the metal, and A is another atom. Now here I can give you a very important material. That material is piezoelectric material. We know this piezoelectric material and ferroelectric materials are very important materials. Sometimes these materials are called the smart materials. Actually, these materials are advanced materials. And why these are called advanced materials, we'll study it when we'll be discussing about material electrical properties of materials. Here I want to give you a brief idea about this. I can give you one example. It is a barium titanate. Barium titanate. This structure will be BaTiO3. BaTiO3. Barium titanate is one of the very, very important piezoelectric material. These piezoelectric materials are used to manufacture the sensor or transducer, because these materials have got some characteristics. You know, if you change the environment, suppose the piezoelectric material is kept in a particular environment, or other types of materials, you know, those are called smart materials because they have the ability to sense the change in environmental conditions, and thereby they indicate what is the type of change, magnitude of change. So basically it acts like, you know, living bodies. You know, when you are giving some stimulus, some input to the living body, they will sense it and they will give you some signal. So that is why these type of materials are called the smart materials, and these are used to manufacture different types of transducer. You know, transducers are those devices which are, you know, used to transform a particular type of signal, input signal, into some output signal. So in those areas, these materials are extensively used. These are basically ionic material. And here we can have 3 different types of atoms. Now just look at this structure here. This is, I have not given any name for this particular material. This can be barium titanate, zinc zirconate, lead zirconate. So there are so many different types of piezoelectric materials. The point is that we have 3 different types of elements here, how they are arranged. So this structure is called the perovskite type of crystal structure, a special type structure with 3 elements. So if we take the barium titanate, it is not written here, but let us say A indicates the barium, M indicates the titanium, O indicates the oxygen. So the formula becomes BaTiO3. O3. So this is the this is the formula. Now what will be the geometry? Just see here the geometry. So barium will be at the corners of the cube. At the corners of the cube. Then comes your titanium, metal. It will be located at the center of the cube, the green color metal. Then the oxygen, this will be at the face center. This will be the geometry. So for almost all these type of, this is one type of structure, and this is related to piezoelectric material. There are some other structure also. So we'll go in detail about this piezoelectric material when we'll be discussing about electrical properties. The cesium chloride, we have already discussed this structure. Sodium chloride, this is not, this is another type of structure we are seeing here. This is another type of structure. Then we have got this SiO2. So there can be so many different types of structures in this also. I have not listed all this. Then another important thing is graphite structure, very important. Graphite, nowadays a lot of work is going on. A particular type of material called carbon nanotube, CNT. It's a nanomaterial, and very lot of research is going on in this area, carbon nanotube. It is basically made of graphite, graphite. So if you go into the detail of this graphite, you know how this graphite forms, graphite sheets are formed. All these black dots are carbon atoms. They form these sheet. There are different layers. These layers are connect. There is a weak bond, van der Waals bond between these layers. So the layers can slide easily. So graphite becomes slippery. But point is that if you see the chemistry of this. So I'm not going into the chemistry because it's hybridization and all that, how this graphite is formed. The diamond for sp3 hybridization and for this sp2 hybridization and all that. So I'm not going into the details. But only thing what I want to just tell you here, that graphite sheets, graphite sheets are formed. Now, the difference between although the graphite and the diamond, you see graphite and diamond made of same carbon atom. Graphite and diamond made of same carbon atom, only there's a structure, there is a difference in the structure. So there's a lot of drastic difference, in their properties. Whether you say it physical properties, whether you tell it, some physical properties or some electrical properties. Graphite acts as conductor. On the other hand, diamond is, insulator. So if you look into the details of the structure, you can get the answer. So what I was talking is that this carbon nanotube, just see, we have studied about the C60 molecule. It forms a sphere-like structure.
Buckminster Fullerens.
Fullerens. So what I am talking about, this B, B, this is in the form of a tube. So it is called a carbon nanotube. First, this graphite sheets are, there's a manufacturing technology, sophisticated technology, and these graphite sheets are rolled in the form of tubes. The point is that these graphite tubes or carbon nanotubes are manufactured, and they have got a very, very high tensile strength, comparable to metals, even more than metals, very high tensile strength. So what is done is that these carbon nanotubes are taken as fiber. Carbon nanotubes are taken as fiber and mixed with your matrix, soft matrix, and thereby you get a light material with very high tensile strength. Now you can think about the application of this type of materials. In aviation industries, where we require that the material should be lighter. So when you are mixing this carbon nanotube with some light, it may be metal or it may be light metals like aluminum, or it may be some polymeric materials. So you can replace some heavy metals with high tensile strength with this, composite materials. Then it will be a composite materials. Matrix mixed with the fibers, it will be a composite materials. That is why I was telling at the very first class that composite materials has got a lot of potential, and in future you see composite materials are going to replace some of the very conventional materials. So a lot of work is going on these composite materials and their properties. A lot of new composite materials are being developed. So carbon nanotube is a very important area of research at this moment, and a lot of research is going on in this area, because these are mixed with different materials to get the different properties, and all that type of work is going on. So here are some polymeric materials, some chains, some diagrams. Yes, here was the diamond structure, diamond cubic initially atomic position. Now, if you look at this diamond cubic cell, it will not be clear actually. It looks like it's complicated. You remember it will be tetrahedral structure, and if you have the idea of tetrahedral positions, you place the carbon atoms at tetrahedral positions, and then it will this type of structure you will get. So diamond structure and Zn structures are same. This you see here in this line diagram, it is shown here, and it is actual diagram. If you see the just actual diagram without this line diagram, it may look very complicated, but you'll have to think about the geometry of the cells. Here is again zinc blend I have already discussed. Here the densities of some materials, some ideas have been given. Achha. So effects of anisotropy. At the very beginning, I was telling that, let us take here a few metal, aluminium, copper, iron, tungsten we have taken, and we are trying to compare the one mechanical property, just to give an indication that how mechanical property changes for different metals in different directions. See, in the particular direction, when you are considering aluminium, this is the elastic modulus. In this direction, it is 72.6. In 112 directions, obviously, if you look at this geometry of this of aluminium, then you will find that in this particular direction, diagonal direction, this comes out to diagonal directions, it is higher. Copper also, then iron we have already seen in one slide, tungsten. So why you see again in tungsten, and then it is almost same. Why it is same? Then you have to look into the geometry. The tungsten geometry I do not have at this moment. You can see the structure of tungsten. Why it is so? Why in all direction? It is actually isotropic. It is becoming isotropic material. So this is a very interesting case. Tungsten, its elastic modulus in this direction or in this direction or in this direction, all the directions are same. This you can see. This is a good example to see why this question is why this tungsten has got the modulus of elasticity equal in all directions. That is the question we should find out. Now here a few just problems I have given. I will send you the PPT. So okay, I have taken this. I have given you as a home task to derive this. You try to derive this relationship about HCP. Then calculate AP density magnesium, assume the data. See, suppose this formula, this question number 1, calculate atomic packing factor density of magnesium, HCP structure. So magnesium has got HCP structure. You collect the value of magnesium, their geometry, the radius of magnesium atom and all that, and try to calculate this. Then question number 2, question 3, consider the ZNS unit cell and the necessary data to determine the following. Number A, position of Zn and S atom, as I have told you. This I am giving you as an exercise. Ionic packing factor density. So these questions you just try to find out the answers of these questions. So this much about, we can go on discussing, but we have got some time limitations, so we'll have to keep it for the time being. Then we have next topic, because the syllabus is quite vast, so we'll have to wind up at some point because of time limitation. The next point we'll be discussing is the
Sir, is this our assignment?
assignment. You can find out the answer. It is not that you'll have to submit it in the form of assignment. You keep it ready for your, for you. Sometimes I may ask some questions related to this in exam or at some.
Okay, sir.
Okay, so you
Okay, sir. Okay.
if it would have been in Blackboard, I would have been shown you some more problems, but I am not ready with these problems. But I'm giving you some problems. Some numerical problems definitely we used to solve a lot of numerical problems in Blackboards. So I'm not giving you those problems. If you want, I can give you. Then I'll have to make ready all those problems. Okay.
স্যার ছবি তুলে নিয়েছি, এটা অসুবিধা হবে না কোনো।
Okay. So next thing is that the topic that we want to discuss. Another 15 minutes I have, because you told that you'll have to leave. You have another class at 1. Another 15 minutes. Just I'll give you introduction on the next topic. So this is actually called the imperfections in solid or defects in solid. This is also very important. Why it is important, that we will try to understand. Defects or imperfection in solids. Our next topic. What happens that sometimes the perfect material, pure crystal do not serve our purpose. We have found that pure materials are deficient with reference to some properties. Then it is obvious that then we require some impure material. We will do some acts of imperfections in those materials, so that we can get some required properties. So intentionally, pure materials are converted into impure materials. I can give you one example. If you take a pure germanium or pure silicon, you know what type of semiconductor you get. You get intrinsic type of semiconductor. So there are some deficiencies in intrinsic semiconductors. So what we do, we perform doping. So we are making the germanium crystal impure by mixing with some suitable atoms, maybe boron or phosphorus, arsenic, something like that, to get the P-type or N-type semiconductors. So this is one example. Another example I can give you, if you take the pure iron, you have, suppose you have using the what is that called, the electrolysis process. You have manufactured a piece of pure iron with no impurities. You will find that the pure iron will not be that useful, because it will have some deficiency so far as the hardness is concerned. You can guess, if you take a pure metal, iron, it will be ductile. It cannot sustain very high tensile load. It will be soft. Toughness will not be that high. It will be malleable. Okay, so we require sometimes we require the ductile material, tough material, strength will be higher, like that. So the pure iron will not serve the purpose. So you know that the ferrous materials are very extensively used almost everywhere, our day-to-day life, or any manufacturing some, or designing, or developing some new types of machine tools. Ferrous materials are extensively used. So you cannot use pure ferrous material, pure iron. So the idea is that it is to be made impure. What we do, we make some element. We are mixing some element with iron, but which is the suitable one? There are so many elements. Why carbon? The reason is that carbon atom can be placed at the interstitial space. We'll discuss it in detail when we'll be discussing about the solid solution and phase diagrams in detail. And it makes a solution, solid solution. But if you take other types of atoms to mix with iron, then you may not get the proper solution, solid solution. That is the idea. So that is also a point to be noted, that which material to be mixed with the parent material. So that is the idea why we intentionally want some imperfect material to serve our purpose. So many of the important materials, many of the important properties of the materials are due to the presence of imperfections. I have explained the idea with 2 examples. Now, next point is to understand is what are the different basic imperfections we have in a crystal geometry or crystal structure. So we say that the crystal imperfections can be classified on the basis of their geometry according to their dimensions. Let us say we call point defects or point imperfections. We call it zero dimensional imperfections, 0D. We have line defects or line imperfections, that is called the 1D. Then we can have surface or plane defects, imperfections, that is called the 2D, and volume imperfection, that is 3D. So these are the different categories. So what are the different types of imperfection? We'll take one by one with examples, and we'll try to see what are the imperfections and their implications. 0D, definitely you have studied these defects in your chemistry, solid structure, solids. So these are called basically the point defects. This can be for non-ionic crystals or ionic crystals. If it is non-ionic crystals, then we classify it into the impurity or vacancy. There is a process how vacancies are formed that we are going to see, because it will be required when we will be discussing the phenomena of solid state diffusion. So vacancy formation for or defects in non-ionic crystals are very important. How vacancies are formed. Impurities also, like when you are mixing some alloying element or dopant in some pure material, then it is called the impurities. It can be interstitial or substitutional. When we'll be discussing about the solid solution, we'll discuss it in detail. Interstitial or substitutional. Then when you're talking about the ionic crystals, it can be Frankel defect or Schottky defect, or other types of defects can also be there. The Frankel defect and Schottky defect you have studied detail. So you know the cases differences between these two. Now vacancy formation, vacancy defects. Why these vacancy defects is formed, and what is the reason behind that? If we want to understand this, these are some of the points that I have just noted down. You can go through, you can understand. So this diagram shows there one atom is missing here somehow. One atom is missing in this diagram. Somehow, how it has gone out and all that point we are not interested. The only thing is that we are interested is that one atom is missing here. So one vacant position has been formed here. So this vacancy is formed, and what is the implications of these vacancies? What is the implications of this vacancy? That is to be understood, and how these vacancies are formed in a pure structure. If the atom would have been here, it would have been a pure crystal structure with no defects. So since here is a defect, it is not regular structure. Some irregularities has taken place here. We call it a vacancy. One atom is missing from here. So what is the reason, and all that will come. Then next comes the impurity, alloying or dopant, or another type. So we know that when a foreign element is added to the parent material or the pure material, then it is called the impurity. So impurity can be interstitial or substitutional. Interstitial, it is, from this diagram it is clear. This, what I was talking earlier, the interstitial space. So this is the regular structure, as we can see in gray color, and then two atoms, this bright color, smaller size, has been placed here at interstitial space. So these are called the interstitial space. What I was telling is that in case of ferrous elements, carbon is very suitable because size of iron atom is comparatively larger to the carbon atom, and this carbon atom takes the interstitial space. So this is a good solution, solid solution. And this is the rule, Hume-Rothery rule. This Hume-Rothery rule will tell you whether two elements will form solid solution or not. So this is also important, whether when you are talking about synthesis of different types of alloys, which are the elements to be mixed to form the alloy, that will be decided by this Hume-Rothery's rule. We will discuss it in phase diagram. We will discuss about this phase diagram. So these are the interstitial types of impurities that has been shown here. And if the size of interstitial atom is slightly larger, some sort of compressive or shear stress fields are developed here, because that the atom that is occupying the interstitial space will try to occupy more space than the normal space. So it will try to move the atoms surrounding it. So a compressive and shear stress field or residual stress, in another way, will be developed within the material, which is not favorable, which we do not want, because residual stress also already makes the material deficient in some properties. So the size of the atom occupying the substitutional position is also very important, and that is why you have to bear in mind this rule, this Hume-Rothery's rule. The interstitial solution, then substitutional, from the name itself quite clear. In case of substitutional solution, what happens, or alloying or type of impurities, what happens, that one atom or foreign element actually replace the original atom and takes that position. So that is how it is, or rather it substitutes the original atom and takes the position. Now size can be varying here. It can be varying. It can vary. So all these rules are there, this Hume-Rothery's rule, to take care whether it will be interstitial or substitutional type of solution. So some examples, 1 2 examples are given. The idea has been shown to you. This is the idea how these metals and alloys are made, and which metals and alloys can be made, and details we'll see in phase diagram. So this is about the impurity. So point defects. Here is some idea how these stress fields are changed, or the you can guess when some vacancies are there, the normal atoms will try to slightly shift towards the vacant side. So there will be some stress fields developed here, or distortion planes will be there within the material. And if there is a extra atom, or we call it self-interstitial, then also there will be some changes. It will be not like normal. In normal cases, if the crystal structure is perfect, these lines, these pink lines will be parallel, or it will be parallel and keep perfect square, something like that. There will be no distortion. So this gives you the idea that if there are certain vacancies or some extra metals occupy the position in the crystal structure, then some distortions will take place or stress fields will be developed. That is the idea, just to give you that idea. Point defects, Frankel defects, Schottky defects, what is the idea. This cation vacancy and anion vacancy together, if it takes place, it is Frankel defect. And then cation vacancy, anion vacancy pair is also known as Schottky defect. I'm not going into the detail of that. Okay, this is the point. How these point defects are developed, and what is the likely number of point defects in a bulk material, in a perfect crystal that can occur. That we'll discuss about a law, and this law, this is a law which is applied in many thermally activated processes. There are certain thermally activated processes like manufacturing of semiconductor, not manufacturing of semiconductor, but this, let us say, thermal conductivity, not electrical conductivity, then this production of point defects. There are so many, phenomena which are called the thermally activated process, and that in those processes, this particular law can be applied. Here also, when we are talking about the vacancy formation, it is nothing but a thermally activated process. As you increase the temperature in a bulk material, there will be a lot of vibration among the materials, and it may so happen that some of the atoms, may escape from the parent material, so thereby vacancies will be formed. So what is the law behind that? This is the law, and here this law will be explaining in detail, and we'll see some examples how this number of defects can be calculated using this formula. So in the next class, we will start from here at this particular slide, and we'll continue. Okay.
Okay, sir.
Okay, sir.
So Sandeep, send me the
Yes, sir.
36 to 34 students. Send me the list. Okay, thank you. Stopping here.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.